Oh, yeah.
I kind of forgot, like, what's the relationship between the potential energy and work?
Oh, the change in potential energy and work. Yeah, it's a matter of. Let's go this way. I think I have do I have a blank energy? Yeah, I have a blank slide there. Yeah. It's a matter of. Well, okay. So first of all, I would say it's a choice of what you decide to use as your system, and your surroundings. Okay. So when you decide to essentially when you decide to choose your system, you can express certain quantities as versus when you decide to put them in the surroundings. For example, if I'm dealing with this bottle, I can choose like say I'm dealing with this bottle. Right there, like in my language, I'm specifying the bottle as the system. Okay. Now, if I want to look at, say, the forces acting on this bottle due to the surroundings, I've identified the bottle as my system, and what would be in the surroundings for that case? Everything else, but specifically, what is interacting? In theory, yes, everything else. We should bear in mind that this distinction of system and surroundings is to help us actually do the problem. Okay? So if you say, okay, the surroundings are everything else, what you're telling me is I have to worry about the interaction of that bottle with the moon, or that bottle and the sun, or that bottle and the Andromeda galaxy that's 2.5 million light years away. You can see where this could be cumbersome. Okay? So go for a spherical cow in space. We don't have to worry about everything because most of the interactions that this bottle experiences are negligible. In other words, compared to some of the significant interactions, the gravitational force between this bottle and the sun is, we don't have to worry about that. Okay. So what objects interact significantly with my system? The table, I agree. What else?
Count the water in the bottle, or is that part of the system?
I was thinking that part of the system. Problem solved. What else? The gravity from the right, the Earth interacts also significantly with it. And then we say we're done. Okay? We have chosen our system, we've got our surroundings, we've only identified the important things in our surroundings so that it makes us able to do the problem. Okay? Now that choice in terms of forces generally tends to be pretty straightforward. Yeah, I mean, like usually in the body of the problem, there's some sort of hint about what you want to choose as your system. Okay? When we go to energy, that distinction between system and surroundings, it's still important, but there's a little bit more flexibility with it. And what do I mean by that? If I'm thinking about, say, I dropped this bottle. There we go. I hope that didn't, well, yeah, okay. So I dropped this bottle. And so I've removed the influence. You can have, if I'm thinking about energy, say if I want to find the final speed of the bottle, I've got a couple of different ways that I could choose. I've got a choice, and either way will make the problem fine to do. Right? Sometimes your choice in system and surroundings has a dramatic effect. If you choose the wrong system and surroundings, it makes the problem devilishly hard to do. Okay? Here, though, when we're thinking about energy, we've got two ways that we can look at it, both of which are relatively the same in terms of difficulty, in terms of ability to do the problem. One choice, sorry, this is a long, you'll have to tell me if I'm beating a dead horse here. So one choice for my system is just the bottle again. Why am I doing this? I don't have a little pop-out thing. There we go. One choice is to do just the bottle, and the other, and have the Earth in the surroundings. And then how we conceptualize that is that the bottle has a force acting on it. Okay? Moving downwards. The displacement of the bottle is downwards. So gravity is doing work on the bottle. And so how does that gravity, the earth, is putting energy into the bottle, and that increase in energy manifests itself as kinetic energy. In other words, the speed of the bottle, what happens? Increases, right? The observable for kinetic energy is the speed. If the kinetic energy goes up, that manifests itself as seeing the bottle move faster. So in other words, we say the work that the earth has done manifests itself as a change in kinetic energy of the system. And we'd have to go through and calculate, the work is the force times the displacement. And is that okay so far? Yeah. So that's one way that we could choose to do it, and that's perfectly fine. You should be able to go through, and the gravitational force is constant, you measure out the displacement, yada, yada, yada. Oh, in fact, yeah, I should ask that. Gravitational force, mg, displacement, delta y, I guess, or maybe I call this a delta h. Call this a delta h, if you want. Incidentally, delta h, let's see here. Oh, wait, we'll put a negative sign in here. There we go. That life will be good. It's called the gravitational force down. Yeah. This delta h will be, let's see, less than 0, because I start out at some initial height and I end up at some final height that's closer to the ground. Right? So then the work ends up being positive and the kinetic energy of the bottle increases. Just ringing bells. I mean, this should feel maybe a little rusty, but hopefully this is kind of ringing bells. And so, yeah, you get a change in kinetic energy here, delta KE. SYS. Yeah, leave that there. Now, that's not the only way to do it. Right? You could, similarly, decide to choose a different system in a different surroundings. Okay? Like I said, sometimes that choice is, there are good choices and there are bad choices. Here, there's a second choice that's completely synonymous with the first. The only thing that changes is how you account for the energy. So what I'll do here is let's put both the bottle and the earth into the system, and I'll put nothing in the surroundings. Well, shoot, if there's nothing in the surroundings, can the surroundings transfer energy to my system? If there's nothing in the surroundings. Survey says, no, right? If there's nothing in the surroundings, the work done by the surroundings has to be equal to 0. It cannot transfer energy to my system. It cannot pull energy away. There's nothing there. There's nothing to transfer to. Is that okay so far? So, if I drop this term, hopefully lights come on, conservation of energy. All right, what does that mean mathematically? I mean, what is conservation of energy? What does that mean about the energy stored in the system? You say energy is conserved. It's neither created nor destroyed. I'll go a little further. I'll say it's neither added nor removed. So if you have zero work, there is no way for you to add energy to the system. There's no way for you to remove energy from the system. In other words, the minute that you set work equal to 0, you can say the energy of the system is conserved. This is a mathematical way of writing down conservation of energy. The change in energy of the system is 0. Energy is neither added nor removed. It all stays inside the system. Now we go and observe. We say, okay, now the bottle and the earth are part of my system. What happens to the kinetic energy of the bottle as I let go? It increases, right? There's a change, right? Right? Hey, the bottle is my system, the earth is in my surroundings. You ready for the experiment? Okay. Now I'm going to put the bottle and the earth into my system and nothing into the surroundings. You ready for the experiment? Fascinating. Right. That's why I say this choice of system and surroundings, it doesn't affect the outside physics. It affects how we approach the problem. It's really a mental kind of division for us to help us get through the problem. Okay. So we know that there's a change in kinetic energy still. There's a change in kinetic energy of the bottle. Oops, there we go. What other form of energy do we now have to consider? The gravitational potential energy, okay? Right, there's a second form of energy inside our system now that we haven't had to take care of. This choice, because the earth is in our surroundings, we don't have to worry about gravitational potential energy. We worry about the force and the work that the earth does on the system. With this choice, we don't have to worry about the work. We set it equal to 0, but now we have to worry about a change in gravitational potential energy. The bookkeeping maneuver. Is that okay so far? Now the changing, I've written down two equations here. Of course, you know the change in potential energy is mg delta H. Right? mgh, and because I have a change, I'm doing a delta H. So you can kind of see what's going on now. Right? Let me go ahead and get the kinetic energy of the bottle by itself. Here I was thinking about potential energy. So I have negative mg delta H. A change in kinetic energy. And over here, I have negative mg delta H. You notice I have the exact same expression now. Two different conceptualizations, two different approaches conceptually, but I end up with the same answer at the end. Now, no! Panic and run! Panic and run! Sorry, too much lion guard. If you have smaller siblings, or if you have like nieces or nephews, they'll get obsessed with these cartoons on this terrible corporation called Disney. And they own everything. And so they'll have zebras that panic and run anytime a lion shows up. There we go. Not a fan of Lion Guard, I see. Not missing much. Okay. Please tell me you've watched The Lion King. Okay, Beauty and the Beast, Aladdin. Okay, there was a class once that they were like, no, we've never watched any of those. I'm like, what the heck is wrong with Little Mermaid? How in the, okay. Started singing A Whole New World, and they looked at me like I grew a third eye. Oh, okay. It wasn't like one person, it was like the entire class. Okay. So you see, you end up in the same spot using two different conceptualizations. Okay. If I wanted to, if I just left this if I go up a line here, so I'll highlight this line right here and compare it with this line. Okay. To answer the final question, so what's the relationship between work and potential energy? You can kind of compare these two lines and see that the work would be equal to the negative change in potential energy. So by moving, essentially by moving the Earth from the surroundings into the system conceptually, all that happens is you replace the work that the surroundings would have done with the change in energy, the negative change in potential energy of the system. Now, incidentally, that substitution only works if you have a conservative force. Right? This is actually the linkage is that, yeah, when you have a conservative force and you're calculating out the work, it's only the starting and final points that matter. And so this linkage only works with the conservative forces. So if you have a non-conservative force, basically you say, well, you can't really write an expression over here. Okay. Yep. Does that get at it for you? Like I said, I know I drop it every once in a while, but like your first semester at PChem will essentially be dealing with this. The change in energy of the system is equal to the work done by the surroundings. You're putting energy into the system, or you're removing it. Right? A lot of ideal gas law in there too, right? I don't know if you do ideal gas law in thermal. PV equals nRT. Pressure and volume are a way of forcing energy into your system. For example, you take a gas, you compress it. Right? You literally increase the energy of the gas. Right? You've done work on the gas. You take a piston and you push it in. You've done work on your system, the gas. How does that manifest itself?
Pressure.
Well, the pressure goes up. What else goes up usually? The pressure is a fancy way of saying force. Pressure is a force per unit area. So if I exert a force, I agree, the pressure goes up. How does it manifest itself in terms of the system, though? You ever done that? You push it real fast, temperature of the system goes up. So you do external work by pushing the cylinder, pressure, you increase the pressure, and what happens is the system responds by heating up. Momentarily, right? If you do it really fast, you can start a fire. Yeah, fire piston? Yeah, it's literally that. You just increase the pressure so fast that you go above the flash point of cotton and it catches on fire. Or a diesel engine works the same way. Diesel? Yeah, man. I was out under the car this afternoon, or on Saturday, changing the oil. But I spilled oil on the spark plugs, which is a big thing. But diesel engines work the same way. Essentially, instead of having spark plugs to initiate the combustion inside your engine, it literally works off of pressure. It compresses it until you get above the flash point of diesel, and the whole thing explodes. So you don't actually need an external spark. It just pressurizes, it explodes. Pressurizes, explodes. Anyway, you should thermal. PV equals nRTs. Carnot cycles. Maybe I'm scaring you. Okay, sorry. I don't know what you do in thermal. Okay. Any questions on that? So again, sometimes somebody comes to me, I mean, this is a common question. What should I put in my system and what should I put in my surroundings? Sometimes it's literally, well, what do you want to put in your system and surroundings? And sometimes sometimes like this, if you came to me and said, what should I put in my system and surroundings? I'd say, well, what do you feel like putting in there? Because it doesn't matter. You'll get to the same answer. Don't put everything. Don't do everything. Okay. Yeah, okay. Oh, yeah, so it's always good reminder. Okay. I don't know if I have very much more to say about potentials, in terms of like the electric potential in terms of calculation. What will end up happening now is we're essentially done with the Coulomb force. We are essentially done with the electric field. You're playing around with the electric potential and the potential energy. And that in itself, I think those two pieces we'll probably keep playing with for a while. The electric potential in particular comes back into play because we want to talk about circuits. We want to talk, we're not in, I mean, yes, it's nice to have this viewpoint, this kind of 30,000 foot overview of what the electric potential really is doing and how, what's going on. But at some point, you want to be able to use a change in electric potential to do something useful, right? And so this is kind of our first foray. We're going to slowly start working towards circuit elements. Namely, you'll see things like capacitors, resistors, Ohm's law, if that rings a bell. And we'll go through and start modeling circuits. Yes, some of it's a little bit toy, like Tinker Toy model-ish, but I found a lot of circuit analysis stuff sometimes transfers over into other things. Well, no, I shouldn't say sometimes, does. Okay. So I'm surprised a lot of the times doing the circuit stuff, sometimes the equations end up looking exactly the same as some other field that you've never even thought of. Okay. So the example I used is I was sitting in on a thermal fluids class for one of the engineering professors, and he sat down and he wrote out an equation, and it was essentially what's called an RC circuit equation, except he was talking about heat flow. So he had a hot item, and he was talking about the resistance of heat flowing through the material. I said, well, that's similar to the resistance of an electron flowing through a metal. So all of a sudden, boom, all the same stuff applied. Okay. Now, again, you'll find these things kind of popping up all over the place. So it's good to just talk about in general. So we'll go into that. So we'll start off, we're starting into that circuit analysis technique, and we're going to be talking about capacitors, resistors, and some fancy things called KVL and KCL. Kirchhoff's current law, Kirchhoff's voltage law, which really sucks because he's just stating the obvious. And he gets two equations named after him. I think that blows. Okay? Like, that's like walking up and saying the sky is blue, and everybody starts saying, hey, Greg's law, the sky is blue. No? Okay. All the low-hanging fruit has been picked, sadly. Okay, so we're gonna have to find something more complicated. Okay, so capacitors seem like it's in a weird spot, and the only thing I can think of that kind of explains why it's in this weird spot is because capacitors are intimately tied to the electric field. Okay. By that, I mean that capacitors operate by keeping charges separated from each other. So when you see a capacitor in a circuit, you can think of it as a device that is built to store charges in a separated manner. So I thought, okay, well, we should conceptually go through how does a capacitor actually do this? And you might see it phrased in a different way. Instead of saying storing separated charges, you might see it as storing energy in the electric field. By keeping charges separated, a capacitor maintains an electric field, which then can be used to move more charges. And I'm already forgetting where I'm at. Okay, so let's do that. If you hear like, okay, well, what is capacitance in reality? You can think of it as a measure of how much charge can be stored by the circuit element. So charge carrying capacity of an object. I will emphasize here, and especially in the treatment for this class, the ability of an object to maintain charge or to hang on to charge is solely what we call a geometric property. So if you're talking about the capacitance of your cell membrane, it only depends on the shape of the cell membrane and the geometry. So, for example, the distance between the outer layer and the inner layer, or the overall shape. If you're talking, well, is your cell spherical in shape, then that will dictate the overall capacitance, the overall ability of the cell membrane to preserve a charge difference. And if you exceed that ability, those are bad days, right? If you get a charge separation that exceeds its ability, then usually you get what's called arcing. I have no idea if that actually happens on a cell or not. Okay. But it certainly happens in everyday life. Okay. You'll have a separated charge that exceeds its ability, and you'll get arcing. Charge will jump from one side to the other. That's usually when you like blow up your computer. Shouldn't say blow up. That's like when your computer starts smoking and then you turn it off and run it. Okay. Usually you blow a capacitor. So what physical properties, what I mean by this, or geometric properties, excuse me. Areas, surface areas, the distance between surfaces, sometimes the radius if you're dealing with a spherical object. I think we'll go through, I'm going to give you one equation, but we'll go through and do it for what's called a parallel plate capacitor. But first of all, I should give you some conceptualization of how this actually works. Okay. Stores energy in the electric field, blah, blah, blah. Disclaimer, what was I gonna? Oh yeah, disclaimer. Probably the scariest thing about capacitors, in my mind, the scariest thing about capacitors, they don't have to be hooked up to a circuit to hurt you. By definition, a capacitor is constructed in order to store separated charges. That is the function of a capacitor. So if you charge up a capacitor, in other words, if you load it up so that it has separated charges, and then you unhook it from the system, the thing that you're using to charge up the capacitor, it still has that separated charge. In fact, so you can pull it out. It's not part of a circuit. It doesn't look dangerous anymore. But if you touch the two terminals, you're going to get a jolt. So that's probably, I mean, I don't say this is scary though. I mean, that's the scary thing I find about capacitors is they don't have to be hooked up to a circuit in order to shock you. So you usually see these disclaimers, right? Unplug device before, like opening it up. Okay? And usually and even nowadays, like they're bricks. You ever notice when you unplug this, that light doesn't go off right away? You ever notice that? What's going on in here, there's a capacitor in this brick. There's some electrical reasons for that. But there's a capacitor in this brick. When I unhook it, that capacitor is still charged. And fortunately, electronics manufacturers are smart enough that they said, well, what happens if some stupid idiot like Greg Robinson someday decides to open this thing up? Well, let's give some indication that all of the capacitors in here have fully discharged. That's why that light doesn't go off right away. They've hooked up the circuit so that once you unplug it, the capacitor runs the light bulb until the capacitor fully discharges. But that's why it says, like you'll see these disclaimers. I don't know if you're going to open up but you'll see, hey, make sure fully de-energized before working with. What they mean by that is make sure all of your capacitors are discharged. You ever see those like handshaky buzzy things? Like, yeah, like you shake your hand, you shake somebody's hand and they like shock you. They have like a little shocky thing on there. That's essentially a capacitor. When you shake your hand, you're bridging the two sides of the capacitor. That's what gives you the little jolt. Or you have the big ones upstairs, right? Don't play with it, because if you open it, the alarm goes off, the ambulance gets called. But it's called a defibrillator. I mean, what's going on there is essentially you have a separated charge and you need to discharge the capacitor quickly, preferably through somebody's stopped heart. No?
Well, I haven't read this, but the defibrillator can't like restart a heart, it like resets its rhythm.
Yeah. So what is it? VFib. If you're in VFib, then you can reset it. But if it's like heart attack, you got to hit it with some, I don't know, not adrenaline, but not epinephrine. You got to hit it with something. Yeah. So if it's like dead, you're like, okay, you're hosed. You gotta something like that. You guys are closer to the medical field than I ever will be. Yeah, I remember. Yeah, like if you're in VFib or something, then you can reset it. But if you're like flatline, then you need something else. ER makes it look so nice, right? You just walk in and, no. I don't know. No, okay, ER is not in the ER anymore. Grey's Anatomy makes it look so simple, right? You just, okay. Let me give you a physical idea about how these capacitors work. That's kind of, I'm talking about capacitors, but what does it really encompass here? Usually you deal with just two plates. I'll think of these as two conducting plates. So I've drawn some wires that lead to the top plate. This wire goes off and it gets connected to some circuit. This wire is completing the circuit. So we'll draw them off screen, but somehow they're getting connected. I don't really care at this point. We'll talk about that later. But you can think of this as a couple stage process. So first of all, these metal plates initially start off as neutral. They have the same amount as positive charge as negative charge. And what I'm going to do is I'm going to connect the wire to some circuit, as I said, which will allow me to start pushing, I'll say positive charges, onto the top plate. I'll do that. Push it onto the top plate. So that top plate becomes now positively charged. It has an excess of positive charges as versus negatives. Sorry, I know that seems kind of goofy. Stupid Ben Franklin, right? Blame Ben Franklin for that one. Because in reality, it's the electrons that move through a circuit, but we don't like thinking about negative charges, and so yeah. So right now I'm thinking of positive charges, but in reality it's negative charges. And negative charges moving one way is like a positive charge moving the other way. So, okay, so I put some excess positive charge on the top plate. Step number one. Next question. What does the electric field do to the top plate look like? If I think about drawing out an electric field now, I've got an excess of positive charges on the top plate. What does the electric field look like around the region of the top plate? I'm sorry?
Being repelled by the top plate.
Well, let's be more specific. I mean, what do you mean by repel?
Like point charges that are positive or whatever.
Okay, the electric field due to a positive point charge goes away.
Yeah.
Okay, I agree. So you could think of, for example, the electric field, I'll think of this point charge right here. You could think of the electric field as emanating away in all directions. I'm just drawing that in for right now. So it emanates away from in all directions. Of course, fortunately, we have a point charge next to it. let's do this one in some color that you probably, I don't know if the contrast will be okay. You have some point charge next to it that is emanating its own electric field. Is that okay? And while we're at it, since I'm off script, I'll call that positive X, I'll call this positive Y, just so we have some directions that we can refer to. Question. Let me think about this field point, say right here. Okay, that's a terrible X. Let me think about that field point for a second. What can you tell me about the X component of the electric fields at that field point? Roughly speaking, qualitatively.
0.
It's
0.
0. Do you kind of see that? Yeah. I said net electric field, you gave a big sigh, like. No, you okay?
Yeah, I didn't sigh.
Oh, didn't you? You looked like you had this momentary. No?
No.
Okay. Okay. Yeah, good. You see that? Hey, because I have this charge right here and I have a nearby charge, you could think of the horizontal components of the electric field canceling, the vertical components adding, the Y components, if you will. And technically the same stuff happens up here, right? I can think of the horizontal things canceling, the vertical ones adding. So one of the cool things about a parallel plate capacitor, now I'm doing this heuristically, but that should be good enough. When you're close to the surface, the net electric field is roughly uniform and in the same direction. You'll notice I've used that in a couple problems when we were dealing with the electric field. I just didn't say anything about it. Go back and look at the deflection of the electron problem. I set up 2 plates with an electric field that was constant between them, and we shot an electron through. Now I'm talking about the 2 plates. I didn't say anything about it in the problem, but that's what I'm doing now. Okay. So it's roughly constant in the same direction. Now I will say, if you get near the edges of the plate, right, you'll start getting kind of right near the edges of the plate, there's no extra charge out here to cancel out the X components. And so as you get near the edges of the plate, the electric field will no longer be constant. It'll kind of bow outwards a little bit. Right? These are called the fringe fields. I'm just giving this to you for completeness. This is called the fringe field. And the big thing you need to know about the fringe field is that we're going to completely ignore it. Okay? We're doing spherical cows in space. We're trying to get an idea about capacitors. I don't want to have to worry about the fringe field. Okay? You might map that in lab tomorrow. It's good to be aware of it, but in terms of calculations and everything else for the purpose of this course, I don't care. Okay? We're going to ignore it completely. Okay? What we want is we want to be thinking about this uniform electric field between the 2 plates. And I don't want to worry about any of the additional complications. I'm not sure if I know how to deal with those additional complications. That's just because it's highly dependent on the shape of the object. So getting the fringe field from a theoretical standpoint is a pain in the rear. Okay? You know it's there, you know, I know how to calculate it, but actually doing the calculation is a pain in the rear. Okay, so we've established that there's a constant electric field, and technically I should draw it on this side as well. Right, there's a constant electric field due to this positively charged upper plate. Next question. If I think about my positive, okay, terrible color, yellow should show up. If I think about my positive and negative charges on this bottom neutral plate, right? I said it was neutral, so there's as many positive charges as there are negative charges. We'll do that. What's now gonna happen? I have this neutral plate that sees this electric field due to the top plate. What's gonna happen to, say, this pair of charges?
Will the positive be pushed off?
The positive will be pushed off. In other words, hey, this positive and negative charge sees this electric field due to the top plate. The positive charges say, I don't like that, we're gonna get away from that thing. The negative charges are gonna say, yay! And they're gonna, sit here on the surface if they can. Right? You can all say it with me, yay! Oh, yippee, yippee. In other words, oh, okay. Well, that would have been nice had we been able to see it because Greg had these junky drawings all over the place. So here we go. We have positive and negatives. The positives move off and leave behind an excess negative charge on the bottom plate. You force charges onto the top. That forces charges to leave the bottom plates and get an opposite sign. So you could have also done it with negative charges, right? You force negative charges onto the top plate, that will force negative charges off the bottom plate, and you end up with one being positively charged, the other one will have a negative charge. You have now separated the charges. And like I said, the thing I worry about is now if you can cut the path, right? Whatever this is connected to, if you just cut it off, now you've managed to store those separated charges. You take that charged capacitor and walk around somewhere else and use it for something. Or you can just lick the terminals and then it discharges through your tongue. Don't do that, but good so far? Questions? That's essentially the physical operation of a capacitor. And then, yeah, this is, we'll refer to this as the parallel plate capacitor. Oh, what, if you ever crack open some of your electronics, I'll see if I can find a picture of one for you, but if you ever crack open your electronics, they don't look like two parallel plates. Yeah. You eat pumpkin rolls? Big fan of pumpkin rolls? Yeah,
Like Swiss rolls?
yeah, like Swiss rolls. Let's say Swiss rolls, right? Think of it like taking two parallel plates and then rolling them up so that you end up with a cylinder, okay? Like a Swiss roll. So if you crack open like the back of your TV, or if you open up your computer case at some point and start looking around, capacitors tend to look like black cylinders. You say, well, that doesn't look like a parallel plate. It's because they took the parallel plates and then rolled it up.
Are they usually like really small?
So that, again, this goes into the physical size of the capacitor dictates how much charge it can store. So physically, yeah, usually capacitors tend to be fairly small, like the size of a dime or smaller in terms of just physical height. Okay? But yeah, I think I have one upstairs that's like the size of a $50, which is, I think it will store a coulomb of charge, which is a lot, right? 10 to the 19th electrons. So if you charge that puppy up, you gotta start being careful with it. Yeah, so the physical size generally dictates how much charge it can store in the separated manner. Other questions? To give you, oh yeah, okay, well, we'll have to talk units, but, yeah, let's keep going. So, so this is the equation I'll give you, without any excess, background knowledge, but I'll give this, so, what this says, if, so I guess I need to label some stuff here. If D is less than A, okay? So first of all, D, is supposed to represent the separation between the two plates, okay? Whereas A represents the area of the plates. What I want to say, if D is much less than A, in other words, the plates are really close together and they're really big, okay? Then the magnitude of the electric field is given by, nuts, okay, sigma over epsilon naught. And now I realize I need to talk to you about what sigma is. So we'll start there. You've probably seen this in chemistry. So I'll try to bank on chemistry here and see. We'll find out. What's on the next page? Nope, that's bad. Okay, sorry, I guess I'll have to do it up here. Unless I get, okay. That's supposed to be a row. If you see that in chemistry, I hazard to guess you've seen that in chemistry. Sorry, looking for the right one. Okay, good. Have you seen that in chemistry? Row? Maybe, maybe not. Blank stairs. Oh, yeah, it's still working, right? Am I on the right? Yeah, that's right. Sorry, I'm just trying to insert a slide here so that I can keep going. Okay, slide. Unless I killed it. Okay, there we go. Mass density. Do you use the Greek letter rho for the mass per unit volume? What Greek letters do you use for mass per unit volume? Do you use Greek letters? No? Okay. Do you remember density? Right, the density of an object is given by the total mass per unit volume.
We just use density equals mass divided by volume.
Oh, so you didn't use a Greek letter at all? Oh, okay. Oh, that's sad. Well, okay, I guess I'll spell it out, but if you can read my chicken scratch. Yeah. Density equals mass per unit volume. Okay. I know in the physics textbooks, we tend to use the Greek letter rho. But that's not the only density you could think of. I struggle to think about mass density kind of thing, but, well, yeah. You could think of something like the density of this piece of paper. And the question I have is, does volume density really seem like a good way to indicate the density of this thing? What might be a better use or better measure of density for this? Area, right? Mass per unit area, right? The piece of paper is so thin compared to the surface that talking about a density in terms of mass per unit area might be a better idea. All right? I mean, unless you want to get your calipers out and measure this. Okay. So then instead of thinking about volume, you can say, well, if I have a 1-inch square of this piece of paper, I hope that wasn't important to somebody, but if you have a 1-inch square of this piece of paper, you can talk about an area density and figure out the mass of this thing based on how much area you have rather than how much volume. Yay, nay? So usually when you're dealing with a two-dimensional object, or one that is approximately two-dimensional, sometimes talking about mass per unit volume isn't the best way to go. Sometimes talking about something like mass per unit area is a little bit more accurate, or a little bit easier to deal with. So you could think of, I guess I'll call this an area density, areal. I don't know what we would call that. I'll call this an area density. This would be a volume density. And of course, if you're following the pattern, you could also think of not a volume density or an areal density. You could think of a distance density, what we call a linear density, right? A mass per unit length. Let's say you're dealing with a rope, right? A really, really long rope, and you want to know its mass. Sometimes it's easier to do a linear density, a mass per unit length. You just measure how long the rope is, and boom, you've got how much mass you've got. So you could also do something called a linear density, which would just be the mass per unit length. Sometimes I think of value, like money instead. It's really easy to come up with something like a volume density for cost, money. Cost per unit volume. Such as gas, right? Gasoline is a cost per unit volume, right? Right now, I think the last time I walked by, it was $2.37. Oh, excuse me, $2.37 with that extra 9 in there per gallon, right? What is this? You're talking about not mass per unit volume, but you're talking about dollars per unit volume. The analogy I draw with that is, can you think of an area density when you're talking about money? Cost per unit area. You think of something where the more area you buy, the more expensive it is. Carpet, right? Flooring, right? Usually, or if you're doing tiling, right, they'll quote you something like, $1.37 per square foot. Right? You're paying money per unit area, cost density, if you will. Or if you're talking about houses, sometimes houses are priced based on the square footage. You're paying $100 per square foot. Or even acreage, land, right? You're paying $10,000 per acre. That's money per unit area. Linear density, let's think cost. Anybody been to Lowe's to buy chain or rope? Yeah, when you go to Lowe's, you buy some chain or rope. What do they do?
The longer it is, it's more expensive.
The longer it is, the more expensive. You walk up, so some of the expensive chains or ropes, they don't actually have it pre-packaged. They have it in bulk. And what you do is you walk up and you say, I need 10 feet of chain, right? My buddy had a good time this weekend and he's off the road. I got to pull him out, right? He went two-tracking, he got stuck. Or mudding, I don't know what they call it down here. We used to call it two-tracking. So you go and get chain, and they say, okay, well, how much do you need? I need 10 feet. And they go, okay, it's $1 per foot. And they'll measure off 10 feet from the bulk stock, they'll cut it, hand it to you. So it's a cost per unit foot. Rope does the same thing. You need expensive rope, they'll just measure it out to length and then cut it and you pay. Okay. So why am I going in this? I forgot my Greek letters. So usually in physics, rho represents a volume density, a mass per unit volume, or something per unit volume. Linear density would be lambda, something per unit length. Whether that be amount of money, whether it be volume, whether it be charge. And right in here, sigma. Something per unit area. In the case in point we're dealing with, we want to deal with the something, the charge per unit area. So I go back to my previous slide, and that's what this sigma represents. It is the charge per area of plate. I found the limit of the Bluetooth. If I stand here, it's okay. If I stand here, it starts getting kind of weird, wonky. So that's what that sigma is in the numerator. It's the how dense the charge is on the plates. Incidentally, because these plates are conductors, when you dump some excess charge on, it wants to spread out uniformly. So for the purposes of this, for the purposes of everything we're doing, you can assume that it is a uniform charge density. It will spread out and be distributed such that the unit, yeah, you get it, okay? If you have the total charge, you have the total area, you can figure out what the charge density is. I gotta talk about this one. And you'll have to refresh me. Did I talk about epsilon naught at all when we were introducing Coulomb's law? I can't remember for sure. That's why I was at. This is just a constant. Okay. So let me, if it's okay, yeah, I guess I'll go down here. This is a constant, epsilon naught, and I'll tell you, this is called the permittivity of free space. Or if you want to put in parentheses, vacuum. It always, there's plenty of things that boggle me. Some things I understand, some things that I don't. Like black holes, they boggle me, but I don't understand them at all. Permittivity of free space always boggles me, but I understand it, sort of. I guess I understand it, but it still boggles me. And so here's the, if you can get past this hurdle, then I think you're good. You ready for it? Empty space is a material. I'll say that again. Empty space is a material. And if that doesn't disturb you, or if you can convince yourself that that's okay, then that's all I have to say about this. Okay. I guess I liken it to, I email Tiff and I say, hey, do you want to go out for dinner tonight? And she never emails me back. Yeah. The lack of a response is a response. Right? If she doesn't email me back, the response is, I guess she doesn't want to go out for dinner tonight. Which would never happen because anytime I offer to go out to dinner, she's like chomping at the bit. We never go out to eat. We're going out to eat. Greg has to get dressed up, find a babysitter for the kids. So the lack of a response in itself is a response, right? Do you want to go out today or tomorrow? No response, that means they don't want to go out. So this is the same thing. The lack of a material in itself is a material. It's a very special type of material that we call vacuum, but it's material. And it turns out that the material, which consists of nothing, does have physical properties. That's the piece that boggles me. Is that, if you think of it as just another material, then of course it would have physical properties. Right? The lack of a material is a material, and that material has physical properties. One of them called the permittivity of free space. Now, if you really want to get into it, come back to 332. Really get into it. Or come into modern physics. Now, just like you have permittivity of free space, you could have permittivity of other materials. You could have the permittivity of air. You could have the permittivity of copper. You could have the permittivity of the lipid bilayer. Okay? So this is just a number that you can put in for whatever is between your two capacitor plates. So we'll talk about it as being empty space, and we'll use the permittivity of free space, epsilon naught. If you want to put a lipid bilayer in between your capacitor plates, then you just have to look up the right value and stick it in for epsilon. Incidentally, epsilon naught free space, if you just see epsilon, then it's the permittivity of a material. You go and look it up in a book. This has a value. I said it's constant. Let me insert another slide here so that we're not. I guess I should have just done that when I started. Let me get this and make sure. Is everybody else okay? Okay, everybody's online still. Okay. Okay, so epsilon naught is equal to, it has a value of 8.85 times 10 to the negative 12. Coulombs squared per Newton meter squared. So epsilon naught is, 8.85 times 10 to the negative 12 Coulomb squared per Newton meter squared. And of course, that unit should look a little bit familiar. Where have you seen that unit before? Yeah, do you remember the Coulomb constant? Right, you remember the Coulomb constant. This looks really familiar. 9 times 10 to the 9th, that was Newton's meter squared per Coulomb squared. Excellent. The Coulomb constant is a shortcut. I shouldn't say a shortcut. I should say it's physicists being lazy. That Coulomb constant is defined as 1 over 4 pi epsilon naught. That's why the units end up the same. In fact, that's how when I'm standing here trying to remember the units of epsilon naught, I'm thinking about Coulomb's law for the force between charges, and I'm redoing it real fast. I know that K has to be this thing, epsilon naught has to be the inverse of that unit. Yeah, so K is a constant because epsilon naught is a constant. Okay, yeah. Questions so far? Yeah.
So what is permittivity itself? Like a property or
You can think of it as how the material responds when exposed to an electric field. Okay. So, yeah, that's how I tend to think about it, is when I take a region of empty space and I apply an external electric field, how does this region respond? The permittivity is closely related to the polarizability, or the ability to polarize an object. Okay, so and it's also related to if I have a material and I expose it to an electric field, how much does the material polarize? And if the material polarizes, there is an induced electric field inside the material. And so that epsilon is a measure of how strong that induced electric field is, due to the polarization of the material itself. So yeah, if you ever run into polarization, if you run into susceptibility, is related to this. How susceptible is the material to the electric field? So, let's see, I'm trying to remember. Insulators have a very low susceptibility, whereas conductors have a very high susceptibility. Conductors respond quickly to external electric fields, whereas insulators will not respond quickly. They won't allow charge to move, in other words. I don't know if that kind of helps or, yeah. So it's a number that you crank and again, it's a material property. The one thing I find fascinating about that number, well, okay, one of the things I find fascinating about this number is it really paves the way for what I'll say is 20th century physics. The fact that empty space has material properties is really weird in itself. I mean, again, the lack of material is a material, but there's something even deeper going on here, and I'll give it to you right now. Although again, we won't get a chance to touch on it in this class, but there's a very weird relationship between a number called the permeability of free space, another material property, related to how it responds to a magnetic field. To be continued. It turns out if you take the permeability, how empty space responds to a magnetic field, and you take the permittivity, how empty space responds to an electric field, and you happen to take the square root of this sucker, you get this really weird number. You get this really weird number that's, well, we'll round it. You get this really weird number that rounded is 3 times 10 to the 8th meters per second, which paves the way for 20th century physics. You guys, 3 times 10 to the 8th meters per second. I see you guys nodding. What is that? That's the speed of light. It turns out that this material property of empty space, this permittivity of free space, is directly tied to the speed of light through vacuum. This also paves the way, this is the tail end of the course, which is why we start off with the electric field. Then we're going to go to the magnetic field, and the last thing that we'll cover in this course is light. Because light is essentially a combination of the electric field and the magnetic field propagating through space, which is why we call light an electromagnetic wave. It's tied to the magnetic and the electric properties of empty space. You're seeing vibrations of the electric field. When you see this light propagating through space, you're seeing vibrations of the electric field.
Electrons change energy.
Yeah. Anyway, hey, thanks for your attention. We'll pick up on capacitors on Wednesday and carry on. No? Stunned silence about light?
Do we have like a date for the exam yet?
Didn't I specify in the syllabi that it would be open from Wednesday to Saturday through Moodle?
I think it's this week or next week.
Oh, shoot. I thought it was next week, but is it this week? Did I have it scheduled for this week? Did I say week 4? Shoot. Well, what do you guys want? Do you want it week 4, or is it going to throw you off to do it in week 5? Huh? I mean, I can open it, yeah, like my intention is to have it in the week specified in the syllabus and just adjust the material to compensate, but I have no problem.
Next Monday, but it'd be better to have it next week.
Do you guys want it next week? Is that? Okay. Okay, then we'll just do it next week. That'll allow us to get that last homework in, so that we can use the electric field and the electric potential on a single exam. So, okay, yeah, okay, yeah, I apologize, I thought it was next week that I had it scheduled.
I wanted to ask at the grade of the first